What is KNN algorithm? Well, K nearest neighbor is a simple algorithm that stores all the available cases and classify the new data or case based on a similarity measure. It suggests that if you are similar to your neighbors, then you are one of them, right? For example, if apple looks more similar to banana, orange, or melon rather than a monkey, rat, or a cat, then most likely apple belong to the group of fruits. All right? Well, in general, KNN is used in search application where you're looking for similar items. That is, when your task is some form of find items similar to this one, then you call this search as a KNN search. But what is this K in KNN? Well, this K denotes the number of nearest neighbor which are voting class of the new data or the testing data. For example, if K equal 1, then the testing data are given the same label as the closest example in the training set. Similarly, if K equal 3, the labels of the three closest classes are checked and the most common label is assigned to the testing data. So this is what a K in KNN algorithm means. So moving on ahead, let's see some of the example of scenarios where KNN is used in the industry. So let's see the industrial application of KNN algorithm, starting with recommender system. Well, the biggest use case of KNN search is a recommender system. This recommender system is like an automated form of a shop counter guy. When you ask him for a product, not only shows you the product, but also suggests you or displays you a relevant set of products which are related to the item you're already interested in buying. This KNN algorithm applies to recommending products like in Amazon, or for recommending media like in case of Netflix, or even for recommending advertisement to display to a user. If I'm not wrong, almost all of you must have used Amazon for shopping, right? So just to tell you, more than 35% of Amazon.com's revenue is generated by its recommendation engine. So what's their strategy? Amazon uses recommendation as a targeted marketing tool in both the email campaigns and on most of its website pages. Amazon will recommend many products from different categories based on what you're browsing, and it will pull those products in front of you which you're likely to buy, like the frequently bought together option that comes at the bottom of the product page to tempt you into buying the combo. Well, this recommendation has just one main goal, that is, increase average order value, or to upsell and cross sell customers by providing product suggestion based on items in their shopping cart, or based on the product they are currently looking at on site. So next industrial application of KNN algorithm is concept search, or searching semantically similar documents and classifying documents containing similar topics. So as you know, the data on the internet is increasing exponentially every single second. There are billions and billions of documents on the internet. Each document on the internet contains multiple concepts. That could be a potential concept. Now, there's a situation where the main problem is to extract concept from a set of documents, as each page could have thousands of combinations that could be potential concepts. An average document could have millions of concepts. Combine that to the vast amount of data on the web. Well, we are talking about an enormous amount of data set and sample. So what we need here, we need to find a concept from the enormous amount of data set and samples, right? So for this purpose, we'll be using KNN algorithm. More advanced example could include handwriting detection like in OCR or image recognition or even video recognition. All right. So now that you know various use cases of KNN algorithm, let's proceed and see how does it work. So how does a KNN algorithm work? Let's start by plotting these blue and orange point on our graph. So these blue points, they belong to class A, and the orange ones, they belong to class B. Now you get a star as a new point, and your task is to predict whether this new point, it belongs to class A or it belongs to class B. So to start the prediction, the very first thing that you have to do is select the value of K. Just as I told you, K in KNN algorithm refers to the number of nearest neighbors that you want to select. For example, in this case, K equal 3. So what does it mean? It means that I'm selecting 3 points which are the least distance to the new point. Or you can say I'm selecting 3 different points which are closest to the star. Well, at this point of time, you can ask, how will you calculate the least distance? So once you calculate the distance, you'll get one blue and two orange points which are closest to the star. Now, since in this case, as we have a majority of orange points, so you can say that for K equal 3, the star belongs to class B. Or you can say that the star is more similar to the orange points. Moving on ahead. Well, what if K equal to 6? Well, for this case, you have to look for 6 different points which are closest to the star. So in this case, after calculating the distance, we find that we have 4 blue points and 2 orange points which are closest to the star. Now, as you can see that the blue points are in majority, so you can say that for K equals 6, the star belongs to class A, or the star is more similar to blue points. So by now, I guess you know how a KNN algorithm works and what is the significance of K in KNN algorithm. So how will you choose the value of K? So keeping in mind this k is the most important parameter in KNN algorithm, so let's see when you build a k nearest neighbor classifier, how will you choose the value of k? Well, you might have a specific value of k in mind, or you could divide up your data and use something like cross-validation technique to test several values of k in order to determine which works best for your data. For example, if n equal 1000 cases, then in that case, the optimal value of k lies somewhere in between 1 to 19. But yes, unless you try it, you cannot be sure of it. So you know how the algorithm is working on a higher level. Let's move on and see how things are predicted using KNN algorithm. Remember, I told you the KNN algorithm uses the least distance measure in order to find its nearest neighbors. So let's see how these distances calculated. Well, there are several distance measure which can be used. So to start with, we'll mainly focus on Euclidean distance and Manhattan distance in this session. So what is this Euclidean distance? Well, this Euclidean distance is defined as the square root of the sum of difference between a new point x and an existing point y. So for example, here we have point P1 and P2. Point P1 is 1, 1 and point P2 is 5, 4. So what is the Euclidean distance between both of them? So you can say that Euclidean distance is the direct distance between 2 points. So what is the distance between the point P1 and P2? So we can calculate it as 5 minus 1 whole square plus 4 minus 1 whole square, and we can root it over, which results to 5. So next is the Manhattan distance. Well, this Manhattan distance is used to calculate the distance between real vector using the sum of their absolute difference. In this case, the Manhattan distance between the point P1 and P2 is mod of 5 minus 1 plus mod value of 4 minus 1, which results to 3 plus 4, that is 7. So this slide shows the difference between Euclidean and Manhattan distance from point A to point B. So Euclidean distance is nothing but the direct or the least possible distance between A and B, whereas the Manhattan distance is the distance between A and B measured along the axis at right angle. Let's take an example and see how things are predicted using KNN algorithm, or how the KNN algorithm is working. Suppose we have a data set which consists of height, weight, and t-shirt size of some customers. Now when a new customer comes, we only have his height and weight as the information. Now our task is to predict what is the t-shirt size of that particular customer. So for this, we'll be using the KNN algorithm. So the very first thing what we need to do, we need to calculate the Euclidean distance. So now that you have a new data of height 161 centimeter and weight as 61 kg, so the very first thing that we'll do is we'll calculate the Euclidean distance, which is nothing but the square root of 161 minus 158 whole square plus 61 minus 58 whole square. And square root of that is 4.24. Let's drag and drop it. So these are the various Euclidean distance of other points. Now let's suppose k equal to 5. Then the algorithm, what it does, it searches for the 5 customer closest to the new customer. That is more similar to the new data in terms of its attribute. For k equal 5, let's find the top 5 minimum Euclidean distance. So these are the distance which we are going to use: 1, 2, 3, 4, and 5. So let's rank them in the order. First, this is second, this is third, then this one is fourth, and again this one is 5. So this is our order. So for k equal 5, we have 4 t-shirts which come under size M and 1 t-shirt which comes under size L. So obviously, best guess or the best prediction for the t-shirt size of height 161 centimeter and weight 61 kg is M. Or you can say that our new customer fit into size M. Well, this was all about the theoretical session, but before we drill down to the coding part, let me just tell you why people call KNN as a lazy learner. Well, KNN for classification is a very simple algorithm, but that's not why they are called lazy. KNN is a lazy learner because it doesn't have a discriminative function from the training data, but what it does, it memorizes the training data. There is no learning phase of the model, and all of the work happens at the time a prediction is requested. So as such, this is the reason why KNN is often referred to as lazy learning algorithm. So this was all about the theoretical session. Now let's move on to the coding part. So for the practical implementation of the hands-on part, I'll be using the Iris dataset. So this dataset consists of 150 observation. We have 4 features and 1 class label. The 4 features include the sepal length, the sepal width, petal length, and the petal width, whereas the class label decides which flower belongs to which category. So this was the description of the dataset which we are using. Now let's move on and see what are the step-by-step solution to perform a KNN algorithm. So first we'll start by handling the data. What we have to do, we have to open the dataset from the CSV format and split the dataset into train and test part. Next, we'll check the similarity, where we have to calculate the distance between 2 data instances. Once we calculate the distance, next we'll look for the neighbor and select k neighbors which are having the least distance from a new point. Now, once we get our neighbor, then we'll generate a response from a set of data instances. So this will decide whether the new point belongs to class A or class B. Finally, we'll create the accuracy function, and in the end, we'll tie it all together in the main function. So let's start with our code. For implementing KNN algorithm using Python, I'll be using Jupyter Notebook Python 3.0 installed on it. Now let's move on and see how KNN algorithm can be implemented using Python. So there's my Jupyter Notebook, which is a web-based interactive computing notebook environment with Python 3.0 installed on it. It's at the launch. Yeah, it's launching. So there's our Jupyter Notebook, and we'll be writing our Python codes on it. So the first thing that we need to do is load our file. Our data is in CSV format without a header line or any code. We can open the file, the open function, and read the data line using the reader function in the CSV module. So let's write a code to load our data file. Let's execute the run button. So once you execute the run button, you can see the entire training dataset as the output. Next, we need to split the data into a training dataset that KNN can use to make prediction and a test dataset that we can use to evaluate the accuracy of the model. So we first need to convert the flower measure that were loaded as string into numbers that we can work. Next, we need to split the dataset randomly into train and test. A ratio of 67 is to 33 for test is to train is a standard ratio which is used for this purpose. So let's define a function as load dataset that loads a CSV with a provided file name and split it randomly into training and test dataset using the provided split ratio. So this is our function load dataset, which is using file name, split ratio, training dataset, and testing dataset as its input. All right, so let's execute the run button and check for any errors. So it's executed with 0 errors. Let's test this function. So this is our training set, testing set, load data set. So this is our function load data set, and inside that we are passing our file iris data with a split ratio of 0.66 and training data set and test data set. Let's see what our training data set and test data set it's dividing into. So it's giving a count of training data set and testing data set. The total number of training data set it has split into is 97, and total number of test data set we have is 53. So total number of training data set we have here is 97, and total number of test data set we have here is 53. All right, okay. So our function load data set is performing well. So let's move ahead to step 2, which is similarity. So in order to make prediction, we need to calculate the similarity between any two given data instances. This is needed so that we can locate the k most similar data instances in the training dataset and in turn make a prediction. Given that all 4 flower measurements are numeric and have same unit, we can directly use the Euclidean distance measure. This is nothing but the square root of the sum of squared differences between two arrays of the number. Given that all the 4 flower measurements are numeric and have same unit, we can directly use the Euclidean distance measure, which is nothing but the square root of the sum of squared difference between two arrays of the number. Additionally, we want to control which field to include in the distance calculation. So specifically, we only want to include first 4 attributes. So our approach will be to limit the Euclidean distance to a fixed length. All right. So let's define our Euclidean function. So this is our Euclidean distance function, which takes instance 1, instance 2, and length as parameters. Instance 1 and instance 2 are the 2 points of which you want to calculate the Euclidean distance, whereas this length and denote that how many attributes you want to include. Okay. So there's our Euclidean function. Let's execute it. It's executing fine without any errors. Let's test the function. Suppose the data 1 or the first instance consists of the data point as 222 and it belongs to class A, and data 2 consists of 444 and it belongs to class B. So when we calculate the Euclidean distance of data 1 to data 2, and what we have to do, we have to consider only first 3 features of them. All right, so let's print the distance. As you can see here, the distance comes out to be 3.464. All right, so this is nothing but the square root of 4 minus 2 whole square. So this distance is nothing but the Euclidean distance, and it is calculated as square root of 4 minus 2 whole square plus 4 minus 2 whole square. That is nothing but 3 times of 4 minus 2 whole square, that is 12. And square root of 12 is nothing but 3.464. All right, so now that we have calculated the distance, now we need to look for k nearest neighbors. Now that we have a similarity measure, we can use it to collect the k most similar instances for a given unseen instance. Well, this is a straightforward process of calculating the distance for all the instances and selecting a subset with the smallest distance value. And now what we have to do, we have to select the smallest distance values. So for that, we'll be defining a function as getNeighbors. So for that, what we'll be doing, we'll be defining a function as getNeighbors. What it will do, it will return the k most similar neighbors from the training set for a given test instance. All right. So this is how a getNeighbors function look like. It takes training dataset and test instance and k as its input. Here the k is nothing but the number of nearest neighbor you want to check for. All right. So basically what you'll be getting from this get neighbors function is k different points having least Euclidean distance from the test instance. All right, let's execute it. So the function executed without any errors. So let's test our function. So suppose the training dataset includes the data like 222 and it belongs to class A, and other data includes 444 and it belongs to class B. And our testing instance is 555. And now we have to predict whether this test instance belongs to class A or it belongs to class B. All right. For k equal 1, we have to predict its nearest neighbor and predict whether this test instance, it will belong to class A or will it belong to class B. All right, so let's execute the run button. All right, so on executing the run button, you can see that we have output as 444 and B. Our new instance 555 is closest to point 444, which belongs to class B. All right, now once you have located the most similar neighbor for a test instance, next task is to predict a response based on those neighbors. So how we can do that? Well, we can do this by allowing each neighbor to vote for their class attribute and take the majority vote as the prediction. Let's see how we can do that. So we have a function as getResponse which takes neighbors as the input. Well, this neighbor was nothing but the output of this getNeighbor function. The output of getNeighbor function will be fed to getResponse. All right, let's execute the run button. It's executed. Let's move ahead and test our function getResponse. So we have a neighbor as 111, it belongs to class A, 222, it belongs to class A, 333, it belongs to class B. So this response, what it will do, it will store the value of getResponse by passing this neighbor value. All right, so what we want to check is we want to predict whether our test instance 555, it belongs to class A or class B when the neighbors are 111A, 222A, and 333B. So let's check our response. Now that we have created all the different functions which are required for a KNN algorithm, so important main concern is how to evaluate the accuracy of the prediction. An easy way to evaluate the accuracy of the model is to calculate a ratio of the total correct prediction to all the prediction made. So for this, I'll be defining a function as getAccuracy, and inside that I'll be passing my test dataset and the predictions. GetAccuracy function, check it, executed without any error. Let's check it for a sample dataset. So we have our test data set as 111, which belongs to class A, 222, which again belongs to class 333, which belongs to class B. And my predictions is for first test data, it predicted that it belongs to class A, which is true. For next, it predicted that it belongs to class A, which is again true. And for the next, again, it predicted that it belongs to class A, which is false in this case, because the test data belongs to class B. All right. So in total, we have 2 correct prediction out of 3. All right. So the ratio will be 2 by 3, which is nothing but 66.66. So our accuracy rate is 66.66. So now that you have created all the functions that are required for KNN algorithm, let's compile them into one single main function. All right. So this is our main function, and we are using iris dataset with a split of 0.67 and the value of k is 3. Let's see what is the accuracy score of this. Check how accurate our model is. So in training data set, we have 113 values, and in the test data set, we have 37 values. These are the predicted and the actual values of the output. Okay. So in total, we got an accuracy of 97.29%, which is really very good. All right.